Welcome, fellow chemists, to Chapter 4 on light and energy. In this chapter, we're going to be dealing with the electrons and not really so much any protons or neutrons. The protons just tell us what element we have, and the neutrons give that element the mass. That's about it. All the action and the excitement is in the electrons. So anytime you see fire, you see some electricity, you see all these different flashes of light and explosions, the action is all in the electrons. So the first thing I want to point out is that light behaves as both a wave and as a particle. So it's kind of a neat thing, interesting thing. It's different from sound. Sound just travels as a wave, but light behaves as a wave and a particle. So one thing we note is that when you have light pass through a prism, it separates into all these different colors. So looks like an old album there. You see white light separated into the rainbow. And here's an actual picture of the prisms doing the same thing. And even a compact disc that's doing the same thing. So kind of old technology there, I guess. Now, one thing that many people don't realize is that you don't always get the full rainbow effect. If you shine a specific element through, it will show some of its own colors. In other words, every single element on the periodic table can be made to separate the colors, and they will show their own unique spectrum. So it's kind of weird to see all those missing colors, but that would be kind of like a fingerprint for an element, and all 100-something elements have their own different fingerprint. Now, we go back up to here. We have light. We're back to what I said earlier. Wavelength and frequency are two variables that we use to do some of our calculations this chapter. The equation, the full equation is here. So the speed of light is equal to wavelength times frequency. And the speed of light is this number right here, 3.0 times 10 to the 8th meters per second. It's something that won't change. And if we go back to our original equation, you can see that we're never really going to calculate C. We're always going to either calculate the first symbol, which is lambda, or the second symbol, which is a symbol for frequency. So, a couple of things to point out. Again, the wavelength is measured in meters, and the frequency is measured in hertz, which is waves per second. Now, here's a picture of wavelength. You would measure it from peak to peak, or I guess you could also go drop to drop. And the correlation here, connection is frequency and wavelength are exact opposites. So if you have a high frequency, you'd have a low wavelength, and vice versa. Now, if you look at this chart, this will be printed on your test, and so it's good to get familiar with it. You'll notice that the X-rays on the far left and the gamma rays over here, these are all the really tiny waves, but they have a very high frequency. So 10 to the 24th, it's almost a mole of waves every second. And 10 to the negative 16th, that's their size. They're billionths and trillionths of a meter, so they're very, very tiny, but there's many of them coming every second. On the other hand, we have these big, gigantic waves, 10 to the 8th meters. So we're talking miles long, huge waves, and you only have one coming by every second, which sounds fast to have that large of a wave coming every second. But on the other end, we have 10 to the 24th, 10 moles of these waves coming by every second. So the energy, all the energy is over here on this end. Now, if you're curious about the speed, they all travel at the same speed, which of course is the speed of light. Now, looking at the visible spectrum, over here the red light is very weak compared to the violet light. The red light has larger waves and has a lower frequency, which means it has less energy. Now, here's our equation for the speed of light rearranged for our two variables. So those are really the two calculations that you'll use for any of the speed of light calculations. The other equation that we're going to use is energy is equal to h, which is Planck's constant. It's kind of like the speed of light. It's a number that won't change, it's constant. And then we see v for frequency again. So that's our second equation that we're going to see. So that means that if we know the frequency, we can know how much energy the wave has. So going back to that equation, we can find the frequency from the chart or from some problem, and we can multiply it by h, which of course is this crazy 6.626 number, and we can find out how much energy is in a particular frequency. So now we're back to the idea that light is a particle, and it's also technically a wave. So we've looked at the wave part, and now we're going to look at the particle part. Here's the photoelectric effect. Electrons get released when light shines on a metal. Okay, so here's a little diagram of it. So right here, we have the waves. So light's acting as a wave, and then in the metal, it's causing the electrons or the particles to move and create some sort of energy. So if we go to the screen right here, we can see with my wave there, the wave would be hitting the solar panel and then causing a flow of electricity through the solar panel. Now if you're wondering how this actually happens, basically an electron hits an atom, and then the electron bounces up and releases a photon of light and then falls back down. So the electrons are basically moving away from the nucleus, bouncing up a level, and then falling back down. So here's a little kind of picture of it. We have right here the electron getting zapped by electricity or some sort of force. Then the electron goes out to an outer level. Then that electron falls back down and releases a photon of light. And then it just keeps going back up and back down and over again. So there's a series of pictures there. Another way of looking at it is this picture right here. We have this electron that's going up to another level, or leaving one orbit and going to the next, and then down here it gives off light and falls back down. So that electron just keeps going back and forth, giving off light and getting excited by all the different things that would excite an electron. So again, electrons absorb energy, they get excited, fall back down, and emit energy. And the technical term for the states, we have the ground state where they're not excited and they haven't absorbed any energy, to the excited state where they have absorbed the energy and they're all ready to release a photon of light. So when these particles give off their light, they each give them off in different patterns. Here's one example of hydrogen and its colors that it would produce. Now this is seen through a spectroscope, which we're going to make soon. What we would see in hydrogen is actually a red light. And here's a few other examples of several different elements and the colors that they emit. So that's it for now. Our next set of notes, we're going to look at all the different models of what electrons do and how they behave.